Hi guys, how are you all doing? And it's Jalajura here again, back with another video from BHM at GCSE Chem. And today we're going to be doing C3.6, which is all about structures, or which is called structures of simple molecules. So C3.6 structures, let me say that again. C3.6 structure of simple molecules. Yeah, that's what it's called. And the book I'm using, let me just show you. It's the GCSE AQA. GCSE AQA or AQA GCSE Chemistry Caboodle book, Caboodle revision guide, and it's the AQA one, like I've said, like I just mentioned. And yeah, so today we're doing C3.6, as I said, and it's all about structure of simple molecules. So that's what we're going to learn about. And just a couple of things. Again, I haven't been able to put the links to my website for C3.2, C3.3, C3.4, and C3.5 as well. So I'll try and do that today. Again, as I said, I'll try and put C3.6 on there as well. I'll try and fully update it on my website, but I can't promise anything. It definitely should be done by the end of this week. If I can't do it today, but yeah. And also, if in the last video, if you thought what I was doing for the last 4 or 5 seconds of the video, basically I thought I ended the video, but I forgot to press stop recording by accident. So yeah, not by accident, but I forgot to press stop recording. That's why you could see my face, see me saying nothing for 4 or 5 seconds, because I obviously thought I had stopped the video. Finished recording, but I clearly hadn't. I did it 5 seconds later, or 4 or 5 seconds later. So that was the explanation for that. So that's the explanation for that. Obviously, and obviously, in my last video, I was back in my normal living room, and again, even in this one, I'm using my my living room to make the video. So yeah, I like this place as well, and also I like my room for recording the videos. But yeah, without further ado, let's begin. So if you're using the student book, which is the big book, the textbook, it's pages 46 to 47 that you want to be on. And so yeah, we're doing C3.6 structure of simple molecules, and then after today we would have done half of chapter 3. So I can't believe there'll still be 6 more sections left after this, but yeah, it's quite a big chapter. But yeah, let's begin. So using models. So you can use models to represent simple molecules. These models are useful, but they do have limitations. Like, for example, also it's very similar to actually when we saw in states of matter, we saw the limitations of the particle model. Now here we're showing here we're talking about limitations of actually drawing different models to represent molecules, using using models to represent molecules. There are limitations, and so most models do not show the actual shape of the molecule. So that's one thing; they don't show the actual shape of the molecule. And also, all electrons are identical. Always you'd have electrons which are identical. But when we're drawing dot and cross diagrams, we obviously use dots for one of the atoms and then crosses for the other atom. We use dots and crosses, which is not actually, how electrons are. Electrons are basically the same. They're all electrons. They should all be the same kind of, they should all be the same. So why do we represent them differently with dots and crosses? So that's another problem. Because we use dot and cross diagrams to show electrons from different atoms, when electrons are all meant to be the same kind of way representation, but obviously we don't do that. And also another problem is electrons are shown in fixed positions, but they are constantly moving. So that's the thing about but they constantly move. So when we draw these, covalently bonded molecules, when we put the electrons, or when we do, even in ionic bonding, basically these electrons are constantly moving. But when we draw diagrams, they're obviously they're static. They're not moving, obviously, because you can't have diagrams moving. Like, that would be silly. You can't show electrons moving on paper. But yeah, that's another problem. So they're the 3 main limitations. So in giant structures, the models only represent a very tiny fraction of a million of atoms or ions bonded together. So when we draw, especially for giant structures, another thing is that the models that we draw only represent a fraction of it, a tiny fraction of the millions of atoms or ions that could actually be in there, that could be bonded together. So for example, there are different types, which are shown here, and I'll run through each of them. You can just trying to show you all of them, basically. Hopefully you can see them and read them there. They're the different types of models there are. And ignore the yellow highlight, like I was doing that for myself doing revision when I was doing my GCSEs last year. But so first you have a 3D ball and stick model. So this is obviously, I don't think, then they're very unlikely to actually ask you to draw structures in 3D at GCSE because that's more of an A-level thing. When they ask you to draw 3D shapes and molecules, that's an A-level chemistry. That's in A-level chemistry, not really in GCSE chemistry. I think they just told you to I think this is just for showing you that this is one way to represent it, and it's actually a very accurate way to represent it. This is how actually they look like, but in this kind of arrangement. But you don't need to know about this much, so don't worry about that. But then you have a 2D ball and stick model. So in the 3D, obviously, you can see there's the bond going down here, diagonal, then here, straight, then here. But in the 2D, obviously, they're all straight. Yeah. So I think this is more likely to come up compared to this one. Yeah. So than this one. So yeah, definitely remember this one. Also, don't really worry about this one. It'd be better to actually remember this one because this one's more likely to come up in the exams. Then the 2D one's more likely to come up in exams than the 3D one. And then the dot and cross diagrams showing outer electrons as circles. So you know this one as well. The outer electrons as circles. Hopefully you know that we've been through that before. And then, obviously, what we could do is we could have dot cross diagrams showing outer shell electrons, but we're not showing the circles here. We're just showing the dots and crosses. So that's another way of representing it. Just this one, and then the final one is using lines. So yeah, displayed formula showing bonds. So we're going to learn more about displayed formula, I think, in chapter 9 or chapter 10 or something like that, in the organic chemistry part of the course of the of the GCSE chemistry course. But for now, just know that a displayed formula is like this, where you have lines basically. Where is it here? It's basically where lines, and basically all of these compounds, all of these represent all of these diagrams are basically representations or different representations of methane. So yeah, CH4, which is methane. So it says here the models used to help us understand the covalent bonding in a methane molecule, and we've been through covalent bonding in the last section in yesterday's video. So then here we have a question: what are the limitations of dot and cross diagrams? So we've been through that. There are 3 main limitations, and actually 4 if you want to add one more for giant structures specifically. But basically most models don't show the shape, don't show the actual shape of the molecules. That's one thing. And for example here, the actual shape of the molecule would be this 3D structure, but for GCSE they'd want you to just know this mainly. This is just to aside on how it actually would look like, a 3D structure. But yeah, I mean, if you want to learn more about it, just to be safe, do learn 3D structures. But it's definitely, it comes up much more in A level. Like I haven't seen much of it in GCSE, so don't worry about that. But basically, the problem with these models are that they don't show the actual shape of the molecule. That's one thing. Like only the 3D structure kind of shows a much more accurate one, whereas 3D ball and stick model, 2D ball and stick model, that's what they're called, ball and stick models, by the way, those 3D and 2D structures I showed you. And another limitation is obviously we show electrons as dot and crosses, but obviously electrons are electrons. They should all be the same. They should all be represented the same way, technically speaking. So that's another limitation. Like they're represented using dots and crosses, which is obviously not very accurate at all. And then obviously another problem is that electrons are sorry about that, just stretching myself. But electrons are shown to be in fixed positions, when you're drawing diagrams, obviously, but they constantly move. It's been a long day, that's why. And also, if you want to add a fourth, especially if it's a 4-mark question or something, then just say for giant structures, the models only represent a tiny fraction of a million of different, atoms or ions bonded together. So that's a fraction of millions of atoms or ions bonded together. So that should be the answer. I'll just make sure I am right. So it does not show the true shape of the molecule. All electrons are actually equal but shown differently on dot and cross diagrams, and also electrons are constantly moving but are shown as fixed on diagrams. They haven't included the giant structure thing for giant structures, but it's good to include that as well for 4, especially if it's a 4-mark question, like a big mark question basically. And then so intermolecular forces now. So substances made of small simple molecules have relatively low melting and boiling points. Covalent bonds are very strong. So we know that substances that are made of simple molecules that have low melting and boiling points, basically. So that's just something to remember, actually. And covalent bonds are very strong because covalent bonds, ionic bonds, and metallic bonds, which we'll go to metallic bonding later in this chapter. But basically, ionic bonding, covalent bonding, and metallic bonding are all these bonds basically. Ionic bonds, covalent bonds, metallic bonds. These are all they're all kind of intramolecular forces kind of attraction, with ionic, covalent, and metallic. But yeah, covalent bonds are very strong. This means that covalent bonds hold the atoms and within a molecule very tightly. So these covalent bonds are very strong. However, each molecule is separate from its neighboring molecules, and so simple molecules have very little attraction for each other. Don't worry much about this. Just remember, this last part. You don't need to worry much about this. But basically, all you need to know is that simple molecules have low melting and boiling points, and that covalent bonds are very strong, and that these hold the atoms together very tightly. So yeah, you don't need to remember I don't think you need to know much about the simple molecules have little attraction for each other. Like, that's not very important, to be honest with you. So then the next point is obviously the forces of attraction between the molecules. Now, between the molecules, you have things called intermolecular forces, which are weak. So these are, the forces of attraction between the molecules are called intermolecular forces, and they are weak. So not much energy is required to overcome them. It is these forces that are overcome when a molecular substance melts or boils. This means substances made of small molecules have low boiling points. So substances that are made of small molecules have low boiling points, and the reason for that is because between the molecules, the forces of attraction that there are basically weak intermolecular forces, and these don't require much energy to overcome, and therefore the boiling point, therefore the forces is these forces that are overcome, and not much energy is required to overcome these weak intermolecular forces, and therefore the substance melts or boils at quite a low therefore simple molecules, or substances made of small molecules have low melting and boiling points. So now here's a question number 2. Which forces are broken when a small molecule melts? Well, it's the weak intermolecular forces that are between the molecules. So that should make sense, hopefully. This is just, again, something you need to remember, a couple of things. Not really, it's not that logical, but it is quite logical, I'd say, but yeah, just something you need to get into your head. I can't do much about it, but yeah, intermolecular forces. I would say the answer is intermolecular forces. I would also say weak intermolecular forces, so they are very, very specific. Just to make sure you get the mark. It's only going to be a 1-mark question, this, in the exam probably, so yeah, most likely. So yeah, now we're moving on to the fact that intermolecular forces increase with the size of the molecules. So larger molecules have high melting and boiling points. So basically, the larger the molecule, the greater the kind of intermolecular forces, the more intermolecular forces it has, and therefore the higher melting and boiling points. So therefore it has higher melting and boiling points. So basically, the larger the molecules, the higher the boiling points, because the greater intermolecular forces there are more intermolecular forces, and you go into more detail regarding this. This really builds up on in A-level chemistry. So yeah, it's really important, especially if you are to take A-level chemistry next year or whenever you're going to do your A-levels. It's very important to get concepts like these, into your head already, because these, I'd say GCSE is basically the foundation for A-level. You need to understand GCSE fully to do A-level chemistry. That's how it is. If you don't understand GCSE chemistry, you're not going to understand A-level chemistry, because it's very, very linked, and it is just basically these topics, but they get much harder, obviously, and they get much, more. There's much more content at A level. But yeah, I don't want to keep blabbering on. So yeah, I just want to say, make sure to understand these topics. It will really help you in your exams, and also it will really help you for future studies if you're thinking to do A level chemistry in the future. In the coming years. So basically, strong covalent bond, weak forces between molecules. So basically, here hopefully you can see a green diagram. I'll just show you, because here, here you have a, let me just see 1 minute. Yeah, I hope I'm showing the right one. Yeah. So here you can see between the black ones are meant to represent the strong covalent bonds, but between the molecules you have these red things, which are the weak intermolecular forces, which are easy to overcome. Not much energy is required to overcome these. So covalent bonds, so in A, so strong covalent bonds, strong covalent bond and weak forces between molecules. So covalent bonds and the weak forces between molecules in chlorine gas. So this is chlorine gas. It is the weak intermolecular forces that are overcome when substances made of simple molecules melt or boil. So when substances made of simple molecules melt or boil, basically these weak intermolecular forces that are between the molecules, they are overcome. And the covalent bonds are not broken. That's very important. These covalent bonds are very, very strong. So you can't break the covalent bonds. What you're doing is you're overcoming the weak intermolecular forces for simple molecules. So that's really, really important. And now, so we've just been through the fact that intermolecular forces increase with size of the molecules. Larger molecules have higher melting boiling points. And just to revise that thing again, just to tell you again, in the diagram I showed you, the black bonds were meant to represent the strong covalent bonds, which you don't break, and the red lines, the red ones were basically the weak forces between the molecules. So they are the ones that are overcome basically when a substance melts or boils. Now we're going on to the next thing, which are polymers. Have very large molecules. They are made of many small molecules that are covalently bonded to each other to form long chains. For example, polyethylene is made up of thousands of ethene molecules. So again, polymers are a topic that we go through in more detail in A-level, not in A-level chemistry. We do go through it in GCSE chemistry as well. We do go through it in A-level chemistry, but we go through it in GCSE chemistry as well, and that we go through it in the organic section of the textbook of the kind of course, which is chapters 9 and 10. I'm pretty sure. Maybe 11 as well, I'm not sure, I don't exactly remember, but organic is basically chapters 9, 10 and 11, and you go through polymers more specifically in chapter 11, so there's a whole chapter on polymers. But basically, polymers, they have very large molecules. They're made from very, very small molecules, which we call monomers. So you can just know that from now. Polymers are very, very large molecules made from very, very small molecules known as monomers. It doesn't say monomers here, but just remember they are made from monomers. It will help you later on when we study polymers. For example, polyethylene is made up of thousands of ethene molecules. So that kind of makes sense. Thousands of ethene molecules make up a very large molecule known as polyethylene. Polymers are solids at room temperature because their intermolecular forces are relatively strong. So just remember that polymers are solids at room temperature. I can't really help with that. You just need to remember that. And then simple molecules do not conduct electricity because there is no overall charge on simple molecules like in a compound like sucrose. So basically, these are just facts you have to remember. The facts are that polymers are solids at room temperature, and it's because their intermolecular forces are, they're relatively strong. These intermolecular forces, and also that simple molecules can't conduct electricity, and because there is no overall charge on simple molecules, like for example sucrose on the simple molecules in a compound like sucrose, for example. There's no overall charge, like it's neutral. That's why. And then here, yeah, here it's just, don't really worry about this too much now, because we're going to go through polymers later on, as I said. But this is basically your long chain polyethene. I think it's polyethene, isn't it? Yeah, polyethene. You can see poly and then square in curve brackets ethene, and then here in here shows the monomer, which is made from many ethene molecules. So again, if it just doesn't make much sense right now, you might have done this before, but if it doesn't, don't worry, we're going to go through it. Just want to show that you can see this is a wait 1 minute. Yeah, this just represents a long chain of polyethene, and this is just polyethene again. Yeah, this is the polyethene. This just N represents the N represents the number of polyethene chains that you have, which are obviously a lot of chains. That's why it's called polyethene. So that's two ways to represent the long polymer chains in polyethene. You can either do it with these brackets and then an N outside, or you could do it like that with just polymer chains, with the straight chains, like that. But don't worry about that too much. We're going to go through that in more detail in chapter 11, which is a long way away from now, but don't worry about that. You might already know this, but don't worry if you don't. So I just wanted to show you the picture. Now here's a question: why does sucrose not conduct electricity? Well, we've gone through that. It's because sucrose is a simple molecule that has, it's a compound with simple molecules that have no overall charge. So there's no overall charge on the simple molecule. That's why. In sucrose, in the compound sucrose. That should be the answer. It has no overall charge on the molecule. Yeah, that's the answer. And you just need to remember that. And then on the up, it says you should be able to explain which forces are broken when a substance containing simple molecules melts. So we know that it's the weak intermolecular forces that are between the molecules. Those are the ones that are broken or overcome when a substance melts, or when a substance containing simple molecules melts or even boils, melting and boiling point, for both. It's for both. And then, here it says, topic for the synoptic link, topic C9.2 gives information on how the size of molecules affects their boiling points. So again, that goes into the organic chemistry and boiling points and stuff like that. We're going to go through all that in C9.2, so in chapter 9. So that's quite far away from now as well. But yeah, the keywords for this section are intermolecular forces and polymers. So they're the key words. Don't worry if you don't know much about polymers. It was just a very, very brief introduction, just introducing it. We're going to go through it in chapter 11. Chapter 11 is purely on polymers. There's a whole chapter on it, so don't worry if you're a bit iffy on that, if you didn't get that at the moment. But yeah, if you do, then that's great. Just the key points to finish off. So substances made of simple molecules have low melting and boiling points. We know that. We've just been through that as well. The forces between simple molecules are weak. We did that the forces are weak intermolecular forces. Remember, these are weak. These are weak intermolecular forces. So these weak intermolecular, sorry, I didn't read it. So let me read it again. The forces between simple molecules are weak. These weak intermolecular forces explain why substances made of simple molecules have low melting and boiling points. So it's because of these weak intermolecular forces that are, relatively easy. They're quite easy to overcome. Not much energy is required to overcome them or break them. It's the reason why simple molecules have low melting and boiling points. And then the last 2 points are that the simple molecules have no overall charge, and so they cannot carry electrical charge. Therefore, substances made of simple molecules do not conduct electricity. There was just a question on that. Why does sucrose not conduct electricity? And I've been through the answer as well. So we know that simple molecules don't conduct electricity because they have no overall charge. And so they have no overall charge, so they cannot carry electric charge, and then therefore they cannot carry electrical charge, and therefore that means substances made of simple molecules do not conduct electricity. Yep, and then models are used to help understand bonding, but each model has its limitations in representing reality. So obviously reality can't be represented. We went through that at the start of the video. So yeah, hopefully that makes sense. And that's the end of this section, guys. I hope it was really useful. It was C3.6 structure of simple molecules. And tomorrow we'll be going through C3.7, which is giant covalent structures, which is another interesting topic. As I said before, I hope this was really useful. Hopefully I'll be able to put obviously I'll upload this on my YouTube channel, C3.6, but hopefully I can also put the links to C3.2, C3.3, C3.4, C3.5, and C3.6. It just tells you, that just shows how behind I am with the putting the links on my website. But I'll try and do that today. If not, everything should be done by the end of the week. So apologies I haven't been able to do it before, but yeah, make sure to share, like, and subscribe. Turn the notifications on, turn the notification bell on if you haven't already, so that you're notified and updated when I upload new videos that you can watch. And I'll see you in the next video, guys, tomorrow, which is tomorrow, and that will be on C3.7 giant covalent structures. Thank you very much, guys.